This contains all the hardware components, on top of which we have created a kernel. Okay, that kernel is running APIs on top of it, which includes Python libraries. Okay, so on top of that we are running the application called Jupyter Notebook. Okay, so this is the framework that we are working with, and this particular Jupyter Notebook is going to work in a similar way as an FTP, and the address for that is 192.168.2.99. okay. So if we want to access the Jupyter Notebook, we need to give that FTP address. Run a couple of more examples today. Okay, so what we have seen yesterday is how do we use Python libraries, how do we use a Jupyter Notebook to dump programs onto the FPGA, and what is the advantage of doing that when compared to using a complete Vivado or HDL or IP based setup, right. The difference we have seen yesterday, it is easier. Okay, it is slightly easier to run it. There are advantages when compared to running the normal flow. We have seen that yesterday. So that is the base level of using Pink, right. We can also run high-end application using Python. Okay, yesterday we have discussed that Python has a lot of built-in libraries, and we can also add our required libraries using Python on the FPGA, right. So using those included libraries or installed libraries, we can run a myriad of applications on top of the FPGA. Okay, there are advantages to doing the same. Okay, we will just have one example to understand what are those advantages and how do we encache those advantages. Okay, so here we are looking at an example, small example of a neural network. Okay, so similar to what we have done yesterday, we can import not only the bit files. So similar to what we have done yesterday, importing bit files, we can also import direct packages using Python, right. So this is an example based on the same. So what I am doing here is simply running an existing neural network, binary neural network on top of the FPGA, right. So this is a very small example of it's a machine learning example, right. I have a data set already built in, and I am doing an analysis with a external image, okay, with an input image. So I just imported the BNN and imported something called as classifiers. Okay. So this is the advantage of using cells here, right. You can see intermediary outputs. What are the classifiers that are available in the BNN that I have already imported, right. You can have a readout of those. Okay. And then I am just importing the data set images from this particular path, right. So I can have these stored readily for my processes. Okay. So these are already stored. Okay. You can see the path here, Jupyter Notebook pictures, right, road signs. So that is the path where all the images are stored. Okay. So all these images are imported, and I and I can run the neural network with this particular data set, right. Depending on the size of memory available to me, I can decide on a larger data set or a smaller data set. Okay. So, I have run it on hardware and I am running it on software as well. Okay. No sir, PS is working, PL may processing will happen. Right sir? Sir, because the BNN library that I am including already is made for the ping board. Yes. So, it is an overlay. It is always an overlay. Right? Import those particular packages, and they most of them will be working for ping board or ping framework. Okay. So, sir, right now we're not working on that. Okay. Yeah. So, this is the image that I want to run my data set against. I am importing that image as well. Okay. I am just reading that image, right? And you can see that it's gone. Okay. Internet. Okay. Ma'am, it depends on our requirement, right? If we are only working with a particular range of images or a particular size of the image is your priority, right? You can check against that. So,
we are not interfacing any PMODs like display peripherals, only monitor will be the.
So you can.
According to that, we can.
Yeah, you can interface not only PMODs but external displays also. So most of the FPGA boards will come with a HDMI or VG.
Displays according to the display resolution, we have to resize the image.
You should stay under the resolution. That's all. There is no. You can go 100% or below. There is no restriction as such. Right? So you can go to the maximum.
As you are displaying this image in the PS processing system, means in the terminal itself, you are not interfacing any PMOD display.
No. No external interface is happening here. I am just using the board for processing.
The image is restricted to our monitor display.
Yes, or the resolution of the image that is already uploaded. That is there in the data set, that is what is the thing. If you are taking live image, then you can define what is the resolution that you want to work with. Right? So, once I have run this particular image, it will tell me that this is what I am recognizing from the data set already imported. So, the data set contains the road sign images. Okay. So, from this the stop sign is being recognized here. So, if I want to get more accurate results, I can reiterate the whole process and get a definitive answer, right. So, regression is also possible. Okay. So, what do we get from this particular example? Okay. What is that we can take away from this particular example? Just a minute. Yeah. So, we can get a definitive answer, right. Reiteration is also possible, that is one thing, and when we run the algorithm both on hardware and software, we can see what is the classification rate that we are getting, right, how many images are getting processed at a particular amount of time. Okay. So, the classification rate for software is 0.628 images per second, right. But when we take the same classification for hardware, we are looking at more than 1093 images processed per second, right. So, obviously, because FPGA has the power of parallel processing, we are able to get such high throughputs, right. Again, this is defined in the filter itself, right. Based on the filter that you are using, you will have different classification rates, right. So, any questions regarding pink in general?
For this experiment, the bit file, yesterday whatever you had
Huh.
shown, was that the same?
Yeah, it will be the same.
So,
It will be the same. But the thing is, we are not using any of the peripherals. Okay, and the bit file is already included within the filter.
can you show where it is included in the
Sir, you see this, the first cell itself, I am importing the complete package for the filter, right? The neural network is completely being imported. So, inside that this will be present.
This is all we are doing inside.
Sorry, sir.
All this we are doing Vivada.
No, sir. This is completely in Jupyter notebook.
No, BNN is doing importing the model, right?
Yeah,
we,
yeah.
We had to train that model.
Yeah.
But how is that including the bit file? Bit file is something to do with.
So I don't need to include the bit file, right? Complete bit file is not required,
Yeah,
because
no, I'm not talking about the complete. Whatever the bit file is, whatever the required hardware is, that's supposed to be included.
that is the thing. Hardware is not.
Packaging and giving like a module to be imported directly. A bit stream everything anta కలిపి ఒక ఇస్తున్నారు ఒక module Python module. When you import and run it, it's running on the hardware.
Same neural network on top of this. See, now it is running on top of this, because this is a simple image. It just went for one single iteration. Okay, but it is possible that you can add your own data set and run it, right? Any other questions, sir? Okay. Okay. So, next thing is going to be STA that we will be discussing. So, how many of you are already familiar with STA? STA, static timing analysis, any kind of timing analysis. Okay. So, for most of you this will be a repetitive class, okay, but we will just bear with me, because that is kind of important to understand why we need that. Sorry? Yeah. So, static timing analysis is a key factor in determining how we can make our designs correct in terms of timing. Okay. There are a lot of processes that you can follow to achieve set timing. Okay, we are going to look at one specific methodology that is called as baselining. That is a technique inside STA that we will be looking at today. So, before we go there, we will just understand what STA is, and there are few common terminology before we enter baselining. We need to understand regarding timing in general. Okay. So, STA okay. So, STA is again a method of analyzing our design for timing correctness. Okay. How is my design performing regarding timing? Okay. So, the primary thing that we need to understand is STA do not require us to give any kind of inputs or outputs. Okay. So, it is never completely a physical verification based methodology. Okay. You can do it.
We should specify timing constraints like rise time, fall time.
Yes, we need to specify, but we do not need to give any physical inputs, right? Physical clock is not required. What we are doing is we are just trying to analyze the timing with respect to some reference material.
Only before synthesis,
No, we need to synthesize the design
after synthesis.
after synthesis, but the thing is we are working on a defined set of constraints already. So, I'll get to that point. So, that is the one thing is no specific inputs are required. Okay, and this can be applied to any of the designs, any kind of design. What do we mean by that? Okay, so let's say we are taking a particular design, and there is always going to be something called as a critical path, right? So, this particular critical path is nothing but the slowest path from input to output, right. How do we decide what is a critical path? Simple, we have a predefined set of delays that the manufacturer will give us. Okay. So, that is our known set of information. So, based on that known set of information, we can calculate the particular delay that is going to happen in any of the paths. So, this is just an example. Okay. So, this is an example where we already know what is the particular delay for each element that is there in the design. Based on that, you can find out what a critical path is. Okay. So, in any of the real time designs, it is not mandatory that there is only combinational paths, right. There will be a mixture of paths, and what we try to do is we try to break them up into groups that are easier for us to analyze, right. So, what we do in STA is we mainly divide our design into 4 different groups or 4 different paths, right. From it is going to be input to reg, which is a register, and reg to reg, reg to output, and input to output. Okay. So, this is how we will look at any kind of design. So, input to a register is one group of paths that we are taking, register to register is one group of paths that we are taking, register to output is one group of paths, and input to output. Okay. It can be pure combinational, or it can also be registered values. Okay. Does not matter, we have categorized all of our paths into groups, right. So, this is the primary thing that STA tells us. Then we have a few different things. For breaking our timing. Okay. So, this is just an example to understand how many different paths can coexist in a single design, right. So, the path 1 is going to be input to register, right. The path 2 is reg to reg, the path 3 reg to output, path 4 is going to be input to output directly. Okay. So, when we are talking about these paths, we need to understand what happens to our timing, right. What happens to my timing, what are the things that can affect my timing paths, right. So, we will be talking about hold time, setup time, skew, delays, right. So, there are a few basic terminologies that we will be discussing now. Okay. Yeah.
In Xilinx flow, is it possible to find directly critical path?
Setup time and there is hold time. Okay. The amount of time that my signal has to be stable before and after the clock is reached, right, that is setup and hold time. So, at the core we will be only concentrating on how much of a setup time violation am I getting and hold time violation am I getting, right. So, overall STA is majorly dependent on setup and hold times. Okay. There are a few more things that are affecting my setup and hold time. So, they are clock skew, jitter, and latency, clock latency. So, these 3 will affect my setup and hold time. Okay. What is clock skew? The maximum difference between the arrival time, okay, of the clock signal to each flip flop, right, that is going to be the clock skew. And then I have the clock jitter. What is the difference between the actual period and the ideal period? That is the jitter that I am getting.
Each arrival, the clock will not exist exactly at the same
Yeah, yeah, at each cycle and at each component. So, every flip flop should ideally get the clock at the same time, but because of the wire delays there will be a small jitter, right. There will be a small shift of the clock to either it can be positive or negative.
issue, we may get jitter.
No, because of
Setup issue, we
yes, yes. So, they always affect the hold time and the setup time, right. So, then comes the latency is generalized delay of my clock because of propagation. right? So there is setup analysis and there is hold analysis. Okay, setup analysis says that the setup time should be would be satisfied if the time taken, the maximum time taken for a clock to reach from one flop to another plus whatever the time is taken inside the combinational path is less than the minimum period of the time required by the clock to reach and the setup minus the setup time. Okay. Similarly, we have the hold analysis where the minimum time required by the clock to reach from flop to flop with the combination in the middle should be more than the hold time, right. So my clock should always reach after, sorry, my clock should reach before my signal reaches the second flip flop, right, and it should stay there for a set amount of time, right. So now comes baselining, right. Baselining is one of the most effective techniques that we can use for any of the designs to correct a time. Okay. There are 3 steps that we will follow when it comes to baselining. Okay. So there are 3 steps that we can follow when it comes to baselining. Simply, step 1 is going to be looking at the internal paths, right, between 2 resistors or inside the combinational path. Okay. So that is what we are doing in step 1. Step 2 is we look at the entire chip after we try to set the timing within a particular path. Okay. Within a particular path, we look at the entire chip if there are any delays that are exceeding my limitations. Okay. That is going to be the second step, to look at the entire chip altogether. Okay. And the third step is going to be fine tuning my design over and over. It is an iterative process. Okay. It is an iterative process. So there are a lot of things, a lot of terminology that we need to understand while doing baselining. Okay. First one is there are multiple types of clocks that we can work with, right. There is actual clock, there is a progressive clock, there is a generated clock, right. There are multiple types of clocks. We need to define what clock is being used for my design, right. If there are any internal clocks, right, if there are any internal clocks, they will not be defined in my design. Huh. Yes, yes, yes. There will not be much of a difference, right. Huh. So there will be some internal clocks, we need to add virtual clocks for those, right. They are not already existing in my design, so I need to give virtual clocks. So there is a command called create generated clocks, right. That is going to be purely internal clock. Okay. Then we have commands to get what my clocks are doing. Okay. So that is report clocks and report clock networks. So report clocks will give us what my particular clock, how is my particular clock generated, what is the time period, what is the breakup of that clock, is the information that I am getting. At the same time, I can also go for reporting clock networks, a complete path from the buffer. So when we talk about 7 series FPGAs, we have 12 clock buffers available to us, right. 12 different regions the clock is getting propagated through 12 different buffers to achieve time. Okay. No, 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 clock buffers. Global clock buffers are there. Okay. BuffG is global clock buffer. There are 12 different buffers there. Okay, it's not. Yeah, vertical and horizontal buffers are divided, are dividing my complete circuitry, complete silicon into 12 different regions, right.
IOs, number of IOs, clock regions.
Huh?
It will divide into the FPGA into clock region.
Regions, yes. Okay. So that is one, and next thing is going to be how do I maintain synchronous and asynchronous clocks. Okay, we can group multiple clocks and multiple clock regions by the command set clock groups. Okay, if it's asynchronous or synchronous, we can group them. Okay, so that is how we do the first layer of baseline, which is internally setting the clocks. Okay, so let's say there is a very long combinational path. Okay, a very big combinational path exists. Okay, inside a combinational path, it is hard for us to correct the timing. We can calculate the timing obviously, but it is hard to correct the timing, right, because we do not have any we only have delays there. We do not have any way to mitigate those delays, right. So there are techniques that we can use by adding resistors in the middle. By registering the clocks and the output values in the middle, we can reduce the length of that combinational delay, in turn reducing the delay itself. Okay. So there are multiple techniques like that. Okay. And one important thing inside this particular clock path, right, a single clock path, is how is my clock interacting inside this path, if there are any loops, okay, if there are muxes available. Okay. So that is going to obviously loop into my design. Okay. So I need to take care of those. How is my clock interacting with other elements in my design is one important thing. Okay. So once I have done all of this, the second thing is going to be optimizing my entire chip. Okay, optimizing my entire chip, which is setting. Ma'am, you can do that, not a problem, or you can design a constraint file directly and add that.
అది డిఫాల్ట్ వచ్చేస్తుంది, బట్ అకార్డింగ్ టు కస్టమైజ్డ్ మనకి కమాండ్స్ అని ఇస్తున్నాం
Uh-huh.
కదా, సెట్ మల్టీ సైకిల్ పాత్, ఫాల్స్ పాత్, మ్యాక్స్ డిలే.
Yeah.
ఆఫ్టర్ గివింగ్ దోస్ ఫైన్ ట్యూనింగ్ ప్రాసెస్, అగైన్ విల్ జనరేట్ ద టైమింగ్ సమ్మరీ అంటాం.
Yes. Uh-huh.
Those are commands where will give the timing.
So yeah, you can do it, or you can create an XDC file, okay, design constraint file, where you are adding these constraints. So basically what these are constraints, right, most of them. Okay, yeah, except for reports, what we are getting out, everything else is a constraint that I am adding. So you can run those constraints in terminal. Okay, in the TCL console you can add those, and once you save your design, they are going back into a single file, which is an XDC, similar to how we have done timing. Yeah. Okay. So once we are done with the singular paths or individual paths, the next thing is setting the entire chip. Okay, checking the entire chip, adding if required any of the delays, either input or output delays, or we can also set that okay, this is the amount of slack that I am giving. Exceptions also can be given. Okay. So after that is done, I'll fine tune my design for any additional loop backs or multi cycles or false cycles that are happening, right. So that is fine tuning. So any kind of multi cycle path delay or false path or maximum delays or exceptions, okay, can be added at the very end. Okay. So there are two steps, okay, that will be running baselining in. One is post synthesis, the second is going to be post implementation. Okay. So implementation is the key factor. Okay. What we are trying to do before implementation or post synthesis is trying to make it easier for the tool to run the implementation and get me the most flexible timing output. Okay, all I am doing before implementation is trying to minimize as much as possible. Okay, the rest which is not happening in post synthesis editing is going to be taken care by implementation, right, because implementation again is placing and routing or components. Okay. Yeah, multi-cycle path delay, that's an example. Yeah, false. Okay. So when we have a multi-cycle path delay, we can obviously reduce that by using some kind of constraints like this. Okay. So I can give the clock name and the period and set that as a multi-cycle path at any given point. Right. In my design, if there exists a multi-cycle path, I can mention that is going to be an exception. Okay. Similarly, I can also do false paths. Okay. So if I this is just a small example here. If I have muxes, so obviously A to path 2, right, is going to be a false path. A to in 1 in mux 2 is going to be a false path. That is never going to happen, right. So I can set all the false paths as well. These are just examples. Okay. Okay. So we'll move on to the tool now. Okay. Just a minute. Close project. Can we open the tool? Okay. All these boards are available. Okay. In ML, in the 2022.2 version, there are more than 100 FPGA boards.
All are advanced boards only, 700.
Yeah, that is what there are multiple boards. Okay, even Arctic 7 there are multiple boards.
Whatever you have displayed are support with tool only.
Yeah, they are already installed in the tool. You can add more boards. That's what we have seen on day 1.
Because Kintex, all these Kintex 7, Kriya, all
Huh.
are advanced.
Most of them are pure FPGAs again, purely for computational power.
Right, sir.
So if your board is supported for this version, even though if it is not installed, you can install it manually. That is what we have discussed in day 1, right. You can add those boards and work on them. Even Ping Z2 board is not directly supported. We have added it, right. So it doesn't matter. There are a few pure FPGA chips that are available to you. Okay. So what we are seeing mostly in the market is 7020 or 7010. So there is a chip zinc, not zinc, 7010 chip, 15 chip is also available. That is mostly for manufacturers. Okay, if you want to manufacture your own board, then that is available. How do people work on that? So you can add those and work. There is no direct board available, right. So things like that also are there.
That
Huh.
I understood, sir.
Okay.
Supporting point of
Yeah. Okay. So you have already downloaded the Ping Z2 lab files on day 1, right? So there is a lab 2 there. Okay. You can add sources. Click on add sources, add design source. Okay. Add design source. Click next. Add files. Okay. And you can go to that particular lab 2 folder.
Just a minute, sir. You have created project and after that you are adding or along with
No, no, no. I have created the project, then I am adding.
That design file.
Yeah, design files, sir. .v files. It will be there in the mail, ma'am. It will be there in the mail. Tawfiq sir had sent a mail, no?
they have sent lab to
Sir, on day 1 you have downloaded a folder called Ping Z2, right?
second system is
Ping Z2. Not the board files. Ping -Z2 होगा तो. Ping Z2.